As you might imagine, it does matter which halogen is leaving as to how fast the substitution reaction will occur. And so here's the relationship. If you look in a periodic table, fluorine is at the top, and that corresponds to the slowest of all the alkyl halides to react. In fact, it's very hard to break carbon-fluorine bonds, so you don't see any examples of alkyl fluorides reacting in this chapter. Chlorine is right below fluorine. It's second in speed of leaving group. Iodide there is the most reactive, the easiest to replace. So again, those are in the order they appear top to bottom in the periodic chart, which is an easy way to keep up with this relationship. And as far as chlorine, bromine, iodine, all of those are routinely used as alkyl halides as substrates in reactions involving substitutions. So for example, in this slide, you can see that we've got a substrate that has both bromine and chlorine. I guess we'd call it 1-bromo-3-chloropropane. And if you react it with a nucleophile like CN, cyanide, and the 1 mole equivalent means you're only adding enough cyanide to replace one or the other, but not both of the halogens. And so the product, the major product, is the one in which you've replaced the bromine because it's a better leaving atom than chlorine. And so that gives us a little flexibility. If we have more than one halogen in a compound, we can choose to replace one of them and leave the other alone. If you add enough cyanide, though, you can press the issue and eventually replace the bromine as well if that's your desire. But it's nice to have some control over things like this. So you need to know the rankings on that previous slide to be able to compare reaction rates involving alkyl halides in which the only difference is which halogen is actually leaving. Another big deal when it comes to speed of reaction is the type of alkyl group you have on the alkyl halide. And these terms here, primary, secondary, tertiary, that goes back to earlier chapters in the book. That was a big deal when we talked about such things in chapter 4, and at the time we were comparing alcohols in terms of them being primary, secondary, tertiary. Here X again is a halogen, but we have reason to do the same thing when it comes to how fast a alkyl halide will react. If all the halogens are the same, if these were all bromides, for example, then it would make a big difference depending on how they're classified, primary, secondary, tertiary. It's not so much a big deal as the total number of carbons or whether they are in a ring versus in a chain, but it really does matter. If you've got a tertiary alkyl halide, it's going to be substituted much quicker than the others. So that's the kind of thing we need to do, is be able to look at alkyl halides and be able to classify them according to this scheme. And that has a lot to do with these two major mechanisms that are at play. These terms were introduced back in chapter 4 as well. SN1 and SN2, they subscript the N for some reason, but that's an abbreviation for substitution, nucleophilic, and then you've got the 1 and the 2 to distinguish whether the reaction mechanism is said to be unimolecular, or bimolecular. That's what the 1 and the 2 mean. So what I'm showing on this slide again goes back to chapter 4, where it is introduced and explained in more detail, but here's the big deal and the thing to appreciate. SN1 reactions are characterized by the creation of carbocations, and you can see in the first step of that mechanism, that's the big deal. We remove the bromine here along with its 2 electrons that it's sharing with carbon, and that creates this tertiary carbocation. Remember, those are the most stable types of carbocations, and so tertiary alkyl halides tend to do just this. And then in the second step, you can get the nucleophile to come in. We're assuming that water is a solvent in this, and so the H2O is literally just a solvent molecule. And so in SN1 reactions, because these carbocations are so reactive, they usually just end up having the nucleophile be a solvent molecule, and so the water adds, making a bond to the oxygen, and then as it says, it loses one of the 2 hydrogens to create the corresponding alcohol. So this is a way to convert the tertiary butyl bromide into the tertiary butyl alcohol. We saw back in chapter 4 that you can do the reverse of this, turn the alcohol into the bromide, so depending on your needs, you can make that reaction go in either direction. And as it says here, if this was a secondary alkyl halide, it would be a very similar thing. Again, the big important step is the first one. If you can create that carbocation, the second step goes very fast and is no problem at all. Down at the bottom we've got SN2, and we'll talk about that a little bit more in the next little video here.